Today we are going to do section 2.3, space curves. So first let's scan the book, okay? And this is the old page already scanned, but I want to show it to you again. Page 70 and 71, okay? Next, page 72 and 73. Uh-oh, let's see. Let me grab this side. There, that should be better. And line this thing up back a little bit. Okay, that should be it. And then zoom in a little bit on top. And a bit on the bottom. Okay. And finally, 74 and 75. Here is the full page. A little closer. Yeah. Okay. And then the top of the page. And the bottom of the page. Okay, so that should be it. Before we start, I want to remind you some stuff from the good old days. Okay, this is the first order differential equation from way back when, calculus 2. Okay, I want to remind you how this is done. That is, here's the page number if you want more details. The point is, let's say you have a first order linear differential equation, which means you have y prime, the derivative, plus pxy equal to qx. The way this solution is solved is by pulling the product rule trick. Okay, you multiply everything by mu of x and then line it up in such a way that eventually you can solve for mu of x by identifying everything line by line with the product rule, which I have written right here. Now, then eventually, because of that, you'll be able to calculate what mu of x is, okay, which is given the equation right here. And then, and with that, you can calculate the equation, what y is. Then the y equation, eventually, the solution to solve the first order linear differential equation is calculating mu of x by e to the integrate p of x. And then your solution is y equal to that stuff over there. Okay, and this is you just know the answer to this part, but I would like for you to see the proof again, because I thought that is how the derivation, this whole part, because I thought it was very neat. Okay, and it's worth looking at again. So so please spend some time staring at this page, okay, all the way to the end. Maybe take a screenshot of it and then go through line by line and refresh your memory on where does mu x come from. I mean, we can just follow the formula at the bottom, but I think this is worth refreshing your memory to see how it works, because it's a simple and yet neat trick, I think, to solve a difficult differential equation. And then on a related note, I just want to mention quickly that, actually unrelated note, I mean, is that remember we have been saying this, that when you switch rows of a determinant, you will get a negative one. Okay, and then if one row is a multiple of another row, specifically if they're the same, then the determinant is going to be 0. And this applies for columns as well. Next, I want to remind you how to solve the second order differential equation. Okay, so, a simple one. That is, the second order equation is where you have y double prime on top here, plus by prime plus cy equal to 0. And the way to solve where a, b, c are just constants. Now, in such a simple second order equation, the way you solve it is you first rewrite this thing like a quadratic formula, and then solve for the roots. Once you solve for the roots, then here's a chart where you dig the solution out of. See, piece of cake, right? Remember doing this back in calculus 3? because I did it a couple months ago and I couldn't remember it at all, and I had to go dig it out because it's so simple, right? You just follow a chart, find the roots of some quadratic, and then you follow a chart, which means I totally forgot it as soon as I was done. So please look this up if you're like me and can't remember how to do this. This will be needed in the homework. So next, I want to remind you what the spherical coordinate is. This is, this is from, all right, this is from Calculus 2 or something, I don't know. Anyway, so the spherical coordinate is defined like this, right? Can you see it okay? All right, so where x is rho sine phi cosine theta, y is rho sine phi sine theta, and so on. And notice how the angles are defined. There's phi goes down from the z-axis, and then theta goes starts counting from the x-axis. And rho is the length, okay? And then, and then the conversion goes something like that. And that should be good enough. And one last thing is that the parametric equation of it to represent the ellipse in the parametric form, I just Googled this, and x is a cosine t and y is b sine t. And just bear that in mind, and if you don't remember later, you know, you can Google it or something. So, so that's that. Okay, so so in this section, we're going to consider something called space curves, stuff that, you know, go around in a line that goes around in space in 3D. So the space curves can theoretically be represented in more than one way. For example, we can represent it as two equations, both equal to 0, that has 3 unknowns in it. They'll end up being some space curve. Okay, and then, or another way, it can even be the intersection of 2 cylinders. Yeah, sure, whatever. And the word cylinder there means anything that is generated from a curve on the ground extended straight up. That's called a cylinder. Okay, that's defined in Calculus, I don't know, 2 or something. So a cylinder isn't necessarily the round one. Okay, it's just any surface that's generated by some curve on the ground, and then you extend it 3D. So anyway, so then, but of course, we're not going to care about that much. And what we do care about is the parametric representation, okay, that we are familiar with from basic calculus. We have the x is represented by 3 components. Each one is parameterized by t or some other thing. Doesn't matter. T is arbitrary, so t can be the arc length s. And then we'll write the equation in vector form where x equal to x of t, which represents all 3 components. Okay, so this means all this together. So so having said that, let's consider example A. Example A is a circle of radius rho, okay, centered at the origin, but it lies in the plane and some plane that's cutting across. Okay, and then and how are we gonna? And the book very kindly drew a little bit of the circle for you. Okay, you know, remember the book is from 1947, and they didn't have Desmos 3D calculator or nothing, so they have to go find an artist who also knows math to draw this stuff out. So then, so then we have the angle. We'll use the central angle, that's the phi on top, okay? That's the measuring down from the z-axis. Now in this book, you notice that x1 stands for the x-axis, x2 is the y-axis, and x3 is the z-axis. All right, so then we have, so this thing, by the time you're done calculating, then you realize the plane is off a turn from x1 at 30-degree angle, I guess. And it's, yeah. It's square root 3 over 3. I don't know. Anyway, isn't it 1 over square root 3 of 1 over square root of 3? Is 1 what? Well, whatever. I don't really care. Actually, maybe I should check. Yeah, it's 30 degrees. Why am I even wasting time thinking about it? Anyway, the point is we have x1 then if the angle T is measuring from the z-axis down, okay, which is called phi or something in the equation I just showed you, and the spherical coordinates, then anyway, so if you work on that, you will quickly find out the x1 and x1, x2, and x3 are as they say. And so please confirm that yourself, okay? And the next thing is if the arc S is chosen, and so if you want to use S as the parameter, that is the arc length, then you just use the rules of a radian, then T equals to S over rho, okay? That is the definition. That is the radius, and the arc length is divided by the radius equals to the angle of, yeah, anyway. So that's that. So please see that make sure all that makes sense to you. And then, of course, I plotted it on the Desmos calculator because nowadays we're way advanced, right? And I can do that, so therefore I will. So as you can see, what does, okay, it looks like that. As you can imagine, there's a what is that? A plane. That is, the red thing is the plane, see? And then the blue thing is the circle that, as you can see, is completely embedded in the plane. So that looks very nice. And then, so if you type in the parametric form like this, okay, and you can totally get it to see the whole thing, not just that little bit that your book shows us. See, once I type this in, it is embedded in that plane like it's supposed to. So the formula is correct. Now, next, let's look at example B, a circular helix. Okay, now again, here we're talking about helix, and the book has conveniently showed you just a very tiny part of the helix. And you're supposed to imagine it. And it is on a circular cylinder, radius rho, and then it goes up and up. Then the helix is given, the helix was covered in basic calculus, 2 or 3, I don't know, remember which. But here's the equation given here, all right, where where the k is some kind of the increase rate. So anyway, so the helix is right-handed or left-handed, depends on, you know, that whether it's increasing as t increases, up or down, okay? That is whatever. So then please read that part yourself to see how the helix goes. And in the meantime, I have plotted this helix out in a case where, where's my helix? Come on, can't find it. Okay, found it. So where the helix is, I choose the rho equal to 1. And then I chose k to be 0.1 because k increases too fast if k is big. So I chose k to be 0.1. So here's my cute little helix, right? And my t goes from minus 20 to 20. And then yeah, so there's my nice little helix. And then I also draw the cylinder on there. You can draw the cylinder by this equation, x squared plus y squared equal to 1. Check the extend to 3D thing. So then that's how you do cylinder. The second it extends to 3D, then the whole thing just shoots straight up. And so then you got the circle extended to 3D, becomes a cylinder, and you notice the helix wraps perfectly around it. Okay, how beautiful. So that is which I consider that so much superior illustration than this thing. Ugh, look at that. You're supposed to imagine the helix out of that. So that's that. And then example 3 is the twisted cubic. This is a curve. You have those 3 equations. And what about it? And the book doesn't say anything about it. That's because I haven't figured out what to say about it either, except to just show you the graph. Where's my twisted something? Okay, here we are. So here's the twisted cubic. Once I plot it into the Desmos calculator, take a look. Yeah, this is from 2 different angles. As you can see, this thing most definitely does not lie on a plane, right? Like the helix is, it goes this way and that way, and then it just shoots straight up and straight down after that, because you have a t to the power 3 there, so it's not gonna stay around too long. It will go clear out of sight. So that is that. Now let's move on to section 3.2, and we have specialized curves. What are specialized curves? We have 3 theorems, okay? And theorem 1 is that the x of t, the one that we're talking about, the what is that? The parametric representation, where x1 is here's equation 1. Okay, it just means the x, y, z, or x1, x2, x3 are all represented by t in the parametric form. So that is equation 1. So what about it? Well, first, equation 1 represents a point if and only if x prime is identically 0. So when you take your formula for x of t in all 3 components, when you take the derivative and it all collapse, that means it can only be a point. Why? Because when you integrate it, then you get a bunch of constants. So x of t equals to constants and is not going anywhere. Okay, it's just stuck on one point. So then it's a constant vector. So yeah. So it represents just 1 point, okay, which is okay. X and t can represent 1 point. Now, secondly, so being that x prime equal to 0 identically, that is equal to 0 no matter what the value of t is, not just a equal to 0 sometimes. So if it's 0 all the way through, then it equals to a constant point. So theorem 2, let's assume it isn't 0. Okay, so then we can go somewhere with this stuff. However, if it is true that look at condition 1 in theorem 2, where x prime of t cross x double prime of t, if it is identically 0 in the range that we're talking about, some range, domain, whatever, in the domain that we're talking about from A to B, then in that case, this equation then the x of t then represents a line segment. So it's a the reason why it's only a segment is because we're only going from A to B, and well, we can feel free to extend it, right? Both directions, past B and before A. So, but in the meantime, at least for A to B, we are talking about a line segment. All right, line means straight line, okay, not any old line. So. So to prove theorem 2, okay, so the next thing, we'll prove theorem 2. So for theorem 2, first let's consider hypothesis 2, where x prime is not 0. Well, by the theorem 1 we just mentioned, okay, that means x prime is, if it's not the null vector, it's not 0, which means, well, by theorem 1 then it isn't just some point, okay? That's so next, hypothesis 1 means that for each t, so we're thinking about t individually, the x double prime is either 0 or it better be parallel to x prime because the cross product being 0. Okay, so for each t, then well, they're parallel or somebody is 0. So being that x prime isn't 0, right? So then the other one, x double prime, has to be either 0 or parallel. And therefore, we can find a scalar function that is for each t, k of t, such that the double prime is equal to k of t multiplied by the first prime, being that they are parallel and all. So then, in fact, because x prime isn't 0, okay, then we can do the division, and then k of t will still be continuous. So far so good. And as a result, now we're going to do something that's from the integrating the first order differential equations that we're going to do. What happens is, first let me show you what equation. Oh yeah, here's the equation we're solving, okay? That is x double prime equals to k of t of x prime. So this is a first order equation because we will solve for x prime first. So this will be so the variable we're solving in this differential equation, it has a second derivative, but we'll consider this a first order. That is the variable, x prime is the variable, we'll solve for x prime, and then we solve for x, okay? So if x prime is what we're solving for, then this is just a derivative of x prime. So we're gonna solve the first order, differential equation, which by the formula that I showed you a moment ago, okay, which I will copy it down right here. which we use this trick with a mu, right? And where mu is e to the power p of x, where the equation is written down right here. Now in our case, q of x is 0. Okay, because our equation is just this, which I rewrote it right here. So p of x is this k of t, whereas q of x is just 0, which means, so then we have the solution then y equals to this stuff, which end up being just y equal to 1 over mu of t times some constant, because q is 0, so we don't have to worry about that part, which is nice. And then, so now we're going to solve each component of x individually, because we're doing the individual differential equations. Now, each component being solved individually looks very similar. They have, so x prime is equal to 1 over mu, which in this case we will call phi. Okay, your book calls it phi, call mu phi. So fine. And then, so x of t then will integrate this thing, which equals to that. So that is, and we'll call this thing, this integral of phi of dt, a new function u of t. All right. So so then in this case, then the a's are not 0. Okay, because if the a's are 0, then x prime of t, which is based on a, that's an a there. I started out writing c and changed it to an a. That's why it looks weird. So a is not 0, or x prime will be 0. Therefore, we rewrite this equation as in the vector form. Okay, it becomes x equal to au plus r. Now that is a line segment. Okay, according to condition M on page 67. That's what we're trying to prove. Now, however, that's a different line segment than what we're used to, because on our condition, on condition M, it says x equal to, instead of u, which is a function of t, it says x equal to, what is that? A times t, right, plus r. And so what happens if it's not just t, but some function of t? Well, so I plotted out an example. I made up u of t. Let's say u of t equal to sine t. Okay, and nice. So that u of t is sine t. What if you have that? And then, but everything else is constant, right? So I'll let a equal to 2 and 3 and 1, and then r equal to 1 minus 2 and 0. So I plotted the line there as in the 3D Desmos, and you can see there's a line. And that one's green because I also, well, what if we don't use u? What if we just use t? Well, that gives us exactly the same line. Except the only difference is for u, as t ranges from 0 to 2 pi, that's all the more sine is going to be good for. Okay, as you increase or decrease t, that doesn't change a thing, which is why the line segment is limited. Whereas if you change u to just t itself, get rid of the sign, okay, and then it's the same line. See, except that now you can increase t to both directions. And so remember, parametric representations are not unique. Okay, you can do whatever. And as long as it works out. So as you can see then that is indeed the line segment as the book claims. And furthermore, it makes an interesting notice that it doesn't in general represent the entire line because the range of u is limited, which in the case I chose, u equal to sine t, most definitely is limited. Okay, so the line segment only goes from a very short section, but we can just represent u of t with t itself, and then we can go forever. Okay, but still it is, despite it being a function, u of t instead of just a simple t itself, it still is a line segment, as you can see. So that is theorem 2. So remember, for this part of the information, okay, please just look through the proof of it carefully and confirm each step. That is, yeah, that's just a matter of applying the formula for the linear differential equation. And specifically, I want to explain that this part is true, okay, and that's because of that's also part of the proof of the mu, which I wrote down right here. See, because d mu of xy equal to this, which is why this formula comes out, and so on. But anyway, so just double check the details and make sure everything makes perfect sense to you. Okay. So theorem 3, we have 2 conditions. First, x prime x double prime x triple prime equals the 0 identically, and then the x prime cross x double prime is not 0 from A to B the whole time. Okay, so then if that is true, then x is a plane curve. A plane curve is a curve that's in space but is stuck on a set plane, kind of like that circle we looked at earlier. Okay, it was a circle but it was stuck in a specific plane in space. And so, and then let's so to prove this, first let's set y equals x prime cross x double prime. Okay. So then next we're going to differentiate this thing. Now to differentiate, how do we differentiate the cross product? This was mentioned in a previous problem that we didn't do because it's tedious and I didn't want to bother, but it's good to remember. Okay, this is on problem 14 on page 66, where it says that the product rule works for both the dot product and the cross product. And you can see why, okay, being that the dot and cross product are done with multiplications and some kind of a subtraction, addition, that sort of thing. So everything carries out nicely. So we're just going to take that as truth, okay? And of course, you feel free to prove that to yourself if you need to. So anyway, so that is basically taking the derivative of two cross products, we'll apply the product rule. But of course, especially with cross products, we need to do things in exact order. Okay, don't flip things around or anything like that. So let's take the derivative of x prime cross x double prime, which I have right here. So here now, y is x prime cross x double prime, okay, and then so y prime applying the cross product is the first. We'll take the derivative of the second one, and then take the derivative of the first one, okay, and then you notice then that the second term is as the double prime crossing itself. Therefore, that goes to 0 because cross product of the same thing goes to 0. So then we'll only have the x prime cross x triple prime left. So that's pretty good, okay? And so that's what y prime is x prime cross x triple prime. And then so next we're going to apply equation 4 a while ago. What's equation 4? I have written down here is the triple cross product, I believe. So the equation 4 I've written down right here so we can compare, okay, it's that thing. So then we are going to cross y prime and writing it down. This is y, I believe, and that's y prime. We'll identify that as r, that's s, and both of these things as t, and write it out term by term, following this formula, okay? So by the time you write it out, please take your time to confirm that I didn't make a mistake, okay? So that's following formula 4. That is, my hand is over here. Okay, so anyway, so please confirm this all checks out. But what you end up with is the dot and cross thing is it's just the determinant, okay, by a formula on the same page. Is the determinant of x prime, x triple prime. Now, anytime you have two columns or rows that's identical, the determinant is 0. So that one is 0. And then over here, this is double prime, first prime, triple prime. What's that? That's 0, but that's given. Okay, we were given this as condition hypothesis 1. See, that's just a given condition right here. So that's also 0. So that's good. So whatever we were doing just now equal to 0, which is how we got this part. All right, so now if that is equal to 0, what does that mean? It means that these two cross products, just like what we just did in the previous page down here, okay, we have, that means somebody is parallel, right? Yeah, just like this thing, see, the same thing. We even use the same symbols. So following this exact same logic, we will copy and paste from here, okay? We're not going to try to understand it again. We'll just copy and paste from here. It equals to kt, which gives yi equals to ai over phi t, and then y equals to a over phi t. All right, okay, so then and next thing we need to mention is that so here it is, okay? We have, I have some of the stuff written down, but it's just a repeat of what we did in the previous theorem. proof. So A is not 0 because the way Y is defined, it is not 0 as given, okay? Because X prime cross X double prime is not 0. That's the given in condition 2. Yeah, C2 there. That's exactly what it says. Okay, so then we have, let me see. So then what? We have then, so next we are going to consider the X prime dot Y. And the reason for that, okay, X prime dot Y right here, which is, if you write it out, that's X, that becomes X prime, X double. Can I even see that? Yep. Is which is equal to 0 because you have two X primes in that determinant. And then down here is identically 0, which is just X dot A, because dot A over phi t, copying from this formula. Okay, so then we can get rid of phi t and just say that X dot A is equal to 0. Now, if X dot A equal to 0, what is that? Sorry, X prime dot A equal to 0. So the derivative dot equal to 0. Now again, from problem number 14 on page 66, remember I mentioned that the dot product applies on the product rule, okay? Applies in the dot product the same way. So then, as you can see, in our case, A is a constant, okay? So, well, then if we were to take X dot A prime, then the second term derivative, this is 0 because A is a constant. So we only have this one. So then we can take the integration to say that if X prime dot A equal to 0, then we integrate these things, and then X dot A must be equal to some constant, and which means that X dot A is in a plane, okay? And so then the plane then so that means X has to be in the plane, and then because in condition K on page 67 gives the plane, anything that looks like a plane looks like this, is at X dot A equals to M, where M is some constant. So that we have proven that theorem 3, that x's that follow these conditions represents a curve that's in the plane. So we have directly shown that it is indeed in the plane, okay? So X dot A equals M, and then that follows the equation, and this is the equation of some plane. All right, so we have come to the end of this section. So for homework, please do problems on page, what page is that? Okay, 73. Problems number 1 to 15. Okay, and then when you're done, I want to talk about them. Okay, so for homework problems, let's see, I think problem 1 and 2 not that much worth mentioning. You just do the basic calculus or parametric and get things to come out. And so problem 3 you have to worry about the ellipse, and the trick is just to remember or dig out that the parametric representation, which I have written over there, of the ellipse. And once that's done, and use the central angle, that is the angle with a z-axis, as t, then everything comes out pretty nicely and quickly once you work out the triangle, okay, which one, and etc., which one goes where. And so for problem 3, I plotted it out. Don't need to, but you know, I just like using the Desmos 3D sometimes. So you see, there's the plane. The orange thing is the plane, and I plotted the ellipse in there, and see, it looks just, it's right there stuck in the plane like it's supposed to. But well, this is just a sample, of course. I chose A equal to 2 and B equal to 1 for the parametric equation of the ellipse, and everything looks nice and beautiful. Okay, so that is, then problem 4, I think, is the twisted cubic. There really isn't much worth saying there. So we just plug it in. That's all there is to it. And then problem 5, similar, okay? We'll choose x1 equal to sine squared, x2 is sine, and so on. And everything also looks okay to me. All right. Okay, next problem 6, we can come up with a parametric representation with cosine and sine and all that stuff and make it come out, okay? Then what kind of curve is that? In other words, is this thing a plane curve or something? So let's look at check theorem 3 to prove that this is indeed a plane curve. What we're going to do is we'll calculate this thing, okay? And then make sure that it is, being that x2 equals to x3, notice the x2 and x3 are the same. So this determinant has two identical rows, which means it's automatically 0. So that condition is satisfied. Next, we calculate the x prime cross x double prime, has to make sure that it is not 0, and it does end up equal to something that isn't 0. Okay, this thing cannot be 0 because rho is bigger than 0. So therefore, this is this thing equation right here, and I think end up you can have a plus or minus in x2, and so you come up with two plane curves, and one spins one way and one spins the other way, and I have it here. Yeah, see, these are the two plane curves. They happen to be on the plane. Well, in this case, it just happened to be if you have two pipes intersecting, which for plumbers, the plumbing parts, you see this kind of thing all the time. Okay, those two curves, and they look like elongated circles, but they're not really ellipses, I don't think. But right now we don't care what they are. We just we're only focusing on whether they are plane curves or not. So that's problem 6. And problem 6 is the same result for a couple of other problems later as well. So then next, let's do problem 7 as soon as I find it. Here it is. All right. So problem 7, I think, is very straightforward. We are supposed to come up with something, so I did, okay? And that is a very quick, simple solution. Problem 8, similarly, I think we're trying to calculate intersections. Being that we have two parametric things, we'll represent this, the twisted cubic, as by s instead of t, so that not to confuse the two t's, because they're not the same, okay? So if we represent it by s, then the fact stands that the second x2 has to be the square of x1, right? Because the twisted cubic requires it. The second component is square of the first one. So that's what I wrote down right here. And now if that is the case, I solve for t, and we got a nice quadratic equation. And when t is 1, it does give us the right answer that fits both cases. t2 doesn't work. So the twisted cubic and whatever that is intersecting at 2, 4, 8, and that's the right answer. So problem 9, we have some line intersecting something. What is it? Who knows? And let's just say they intersect. Now for that to happen, then I guess we'll just plug it in, okay? Plug the t's into x's and see if something comes out, and we end up with this horrendous looking thing with the power 8. So what I did is I used the factor calculator. I include the link in the video below, okay? I just plugged it in the calculator, and out it says it only has t equal to 1 as, I don't know, a double root or something. And so once t is 1, then it becomes 1, 1, 1. That's where it intersects. And that's all I'm going to say about that, okay? And so next, let's look at problem 10. Let me see, does problem 9 say anything else? Yeah, that problem 9 gives a big, long, painful hint. That's because back in the day when they didn't have a factoring calculator, which we do now. So let's ignore that hint, okay, and move on. And so problem 10, we have an interesting problem that's similar to what I mentioned earlier. Okay, we have a sine t, and then try to figure out what is that thing. Well, if you being the sine t is in every single component, I just let u equal the sine t. And then what is that? That is just the line, right? And then except that in this case, u is limited between -1 to 1, but that's okay. It's and it is a line segment. And furthermore, it satisfies the condition of what does it want? This is problem what, 10? Yeah. Notice the hypothesis 2. Well, yeah, and I checked that it satisfies hypothesis 2 or something, and in terms of sine t, then the hypothesis 2 isn't satisfied. sometimes. Well, but condition 1 satisfied. If you call it sine t, then hypothesis 2 sometimes isn't satisfied, but that's okay. We don't really care. I mean, why call it sine t when it can just be t? And so anyway, the point is that thing is a line, and that's good enough for anybody. Okay. And then that is problem 10. All right. Next, problem 11. Problem 11 is the same as problem 6 because you notice that e of t shows up in all components. So let's let u equal to e of t. And then you notice that that looks identical to problem 6, which was that the pipe intersection thing. Okay, so we have two curves, two enclosed plane curves that look sort of like ellipses but aren't, or something. And so those are just, that's problem 11. So problem 12, we have, problem, give me a second, did we done 11? Yeah, we did. Okay, so problem 12 says that if the determinant x prime, x double prime, x triple prime is identically 0, it show that this is true if x is a plane curve. So we're doing the opposite of something, the theorem 3. To do that, then we'll work backwards from theorem 3. Okay, we have first, being that it's a plane curve, sum a will be equal to some constant, or we can write it this way. The dot product is written down like this, which means we can represent x1 in some combination of x2 and x3 plus some with some constants. So we'll write it as some kind of replace the constant as b2, b3 to be a bit simpler. And similarly, for x double prime and x triple prime, which I have written everything down here. So then when you calculate that determinant that we're looking for, we have, we can write it down. Being that they are pluses, we can split it into two determinants, okay? And so then being added together. And look carefully that the first, then the determinant here becomes b2 times the second row, and then b3 times the third row. And whenever you have one row that's the multiple of some other row, then the determinant are automatically 0. So each one of these things are 0. So together they are 0, and therefore that triple, this thing right here, the determinant that we were looking for, is also 0. And that's the end of this problem. Next, let's consider problem 13. What is x if x is not 0, but x cross x prime is 0? So we are going to use theorem 2. The problem is, of course, theorem 2 only talks about x prime cross x double prime. So how are we going to get around that? We're going to pull a trick. Okay, we will let y prime equal to some y of t such that y prime is equal to x of t. All right, so then we can use theorem 2, because then y double prime will be equal to x prime, and then y prime is not 0, okay, because x is not 0, and then y prime cross y double prime is identically 0, okay, given, okay, and also satisfies the theorem 2. Therefore, that by theorem 2, then y of t is a line segment. All right, so if y of t is a line segment, which means that y is equal, y minus r equal to ta, okay, by condition m on 67. And then which means if we take the derivative of this thing, y prime of t is just some constant a, okay, which equals to x of t. In other words, x of t is 1 point, a. That's it. I thought this is a nice little problem because it allows us to use theorem 2, and yet there's a twist in it, okay? So problem 14 is an easy version of problem 13 or something. And we have, so if we have a straight line, we know that the a cannot be 0. Okay, otherwise it wouldn't be a line anymore, it'd just be a point. X prime is, so then x prime is a, which means x double prime is going to be 0. Okay, being the a is a constant vector. And then prime cross double prime is going to be 0, which satisfies the conditions for theorem 1. And that's about it. Okay, so let's look at the next problem, which is more interesting. We have some kind of a thing here, and we have to figure out something. We have two conditions. Okay, we have x1 given as cosine t, x2 is sine t, x3 we don't know what it is, but we have to control it in such a way that f of t has to be chosen such as that this thing then becomes a plane curve, which means it has to satisfy theorem 3, of course. Theorem 3 has two conditions. The first one is, well, the second one or something, whatever it is, it says the cross product has to be 0. And that is, has to be not 0, sorry. Right? It says the theorem 3, let me make sure to show you the conditions. Yeah, the first one is says the determinant has to be 0, but the cross product cannot be 0. Okay, so the cross product not being 0 comes out pretty readily because the k component happens to have a 1 as in front of it, which means it will never be 0 because k is at least 1. Okay, so that's that. And then, but the other condition, that is the triple derivatives determinant has to be 0. So we'll write this thing out, okay, and then calculate this thing, which conveniently end up being this, okay. And if we develop the determinant along the bottom row, doesn't really how you do it. I mean, how you do it really, but this seems a little faster. And so then we get this particular equation, and that's the third derivative. But luckily we don't have anything else here. So then if we let y equals to the first derivative, we get a second order equation, which I mentioned before. Okay, and the solution to that I showed you in the beginning of this video, or you can just dig it out yourself somewhere. It is, I have it listed here as well, is in the Calculus 3 book, in those pages. And then once you notice that, you calculate the lambda, which happens, which is corresponding to this as a quadratic equation. And lambda is just plus or minus I, which means y equal to c1 cosine x and c2 sine x. So f being f is the y is well, f and y has f, you just integrate y, okay. So then integrating cosine and sine, you get the same thing, except that now you got another constant. So f of t is equal to some combination, linear combination of cosine and sine plus a constant, and that would be good enough. And that we have come to the end of this section.